It's been around a week since I posted that other video, and I've been wondering if this is the best way to make these kinds of videos. I mean, the last video was kind of lengthy with some unnecessary solutions, so I suppose the next one is only gonna have one solution than my own experience with it. This isn't mainly an educational channel, rather more of a documentation series. Actually, I just don't know though. I've been thinking about it for so long that my thinking table is getting tired. But that's not stopping me any—
You've got mail.
Mail? Oh, solve the second problem, right. So, the second problem was the learning experience. At first, I didn't think it was going to be anything special until I read the Euler forums. There was one comment in the top that was proof regarding on how— never mind, that's a spoiler. You can only know that when I realized what it was trying to do, it was brilliant. I found that there was a lot of solutions or ways you can get the answer. Don't expect this video to have concrete solutions, but rather basic insights to show you how amazing this sequence is. And yes, spoilers ahead. Link in description for the original problem. Problem 2 prompts you to find the sum of all even-valued Fibonacci terms that do not exceed 4 million. Well, that's it. The first thing I did was to do the most obvious solution, which was to make a loop that would generate Fibonacci terms and would check if the current term was divisible by 2 so that I would add it in a sum variable. That worked and I felt lazy. Here's the thing, the first couple of Fibonacci numbers are 1 and 1, and as you notice, they are both odd. If we were to add odd numbers, logically we would get an even number. 1 plus 1 is equal to 2. We add an even number to an odd number to get an odd number, and then an odd number to an even number to get an odd number. You probably know where this is going. There's a pattern going on to determine which numbers are even numbers, and that's every third term of the Fibonacci sequence. So that means just tell the computer to generate Fibonacci terms and adding the third terms only. You don't even need to worry about a lot of computation for this, considering the last terms that exceed 4 million is the 38th term, which means 38 iterations at most. I would stop here, but I seek a more general approach that lets me calculate all even value Fibonacci terms that don't exceed another higher value, let's say 4 trillion. I don't know how many values are in there, but I'm guessing there is a lot, and that requires a lot of calculations for larger numbers. And we have to be precise on that too. My first mistake with it is not to be precise using an approximate constant. I'm talking about the golden ratio depicted as phi. Consecutive terms of the Fibonacci sequence are in a ratio depicted like so. The nth term of the Fibonacci sequence divided by the nth minus 1 term of the Fibonacci sequence is equal to 1.618033988 and so on. But you're probably wondering, the first couple of terms, 1 and 1, don't fit this. You're right, it doesn't. Here's a more precise definition. As n approaches infinity, we can see that f of n divided by fn minus 1 is equal to the golden ratio. The larger the numbers, the more precise the ratio becomes. If we were to multiply a term of the Fibonacci sequence with the golden ratio, we would get the next term. It's not exactly the next term, so we need to round it. Keep in note that this isn't really precise as we get to larger numbers. You'll see what I mean when we get there. If we were to multiply that term again with the ratio, we would get the next term after so. What that means is basically we can just multiply the square of the ratio on one term to get ahead of the sequence 2 terms to the right. With this logic, we can multiply the cube of the ratio to get the third term from the right, which is what we can do to get every third term of the sequence. My solution was to make a loop that would generate every third term of the sequence by multiplying the current term to the cube of phi. This solution would work until this happened. It seems that it calculated an odd number. How odd? I figured that it's probably because of my phi constant, which has only been reduced to a few decimal places. I figured that if I expanded the decimal places, the number would be more precise to calculate. I gathered some more numbers from the OEIS and then tried to see if it did anything. It stopped becoming an odd number, but there was one more problem, which was the last term that I needed. The last term was an even number, but it wasn't a Fibonacci number with a difference of 4. What happened? I can't even see the decimal places because of how the number is stored. Well, I tried adding some more decimal numbers, but that didn't work. There was one solution or a way to get every third term of the Fibonacci sequence, and it's stated in the Project Euler problem overview that is only available after finishing up the problem. I'm not going to tell you about it, but it's absolutely brilliant, and I recommend you solve the problem yourself to get a look at it. It worked because it was precise and I didn't have to rely on the values being wrong. So yeah, it took me a while, but I got through. In conclusion, I don't trust the word approximate.